So we have a table here of the speed of sound in various different media. First we have two gases, air and helium. We can see that the speed of sound in air is about 343 meters per second. So that means that every second a sound wave can propagate across 343 meters of air. This is assuming that we're at standard temperature and pressure. That is 25 degrees Celsius at normal 1 atmosphere pressure. So now let's take a look at some liquids, mercury and water. As you can see, because liquids are so much more dense than gases, sound waves will travel far more quickly. So these speeds are about 1,500 meters per second, which is 4 or 5 times faster than the speed of sound in air. So we can see that in liquids, sounds will travel much more quickly. That means that if you're underwater and you hear a sound, you'll hear it more quickly than if the source of the sound was above water, and so are you. Because if both the source and you are above water, then the sound will propagate through air at a relatively slow 340 meters per second. But if you and the source are both underwater, that means the sound wave will propagate through the water at a much faster 1,493 meters per second. Alright, so how about some solids? We can see that most of these solids have a propagation speed that is even faster than mercury and water. So of course, metals will have different densities, usually greater densities, and also different elasticities, which explains why there's so much variation between them. In general, the harder solid is, the more quickly it will allow sound to propagate. So we can see right at the bottom that sound will propagate through diamond at a speed of about 12 kilometers per second, which is far faster than for any of the other media here. Two pulses of sound are sent toward a receiver. Fairly straightforward, right? Now one travels through air at 340 meters per second, and the other travels through water at 1,490 meters per second. Calculate the delay between the two signals if the receiver is 500 meters away. So in this case, we can see that the sound wave that travels through air, because it can only go 340 meters per second, won't actually be able to reach the receiver in the first second. Whereas the sound wave that goes through water will be able to reach the receiver in probably about a quarter of a second. So what we're looking for is the delay between these. And how do we figure that out? Well, distance over time. So the pulse that goes through water takes a time of distance over velocity equals time, 0.34 seconds. This formula you probably should know by now. If velocity equals distance over time, that means that simply by multiplying both sides by time and dividing both sides by our velocity, we get time equals distance over speed, right? So if we're going to follow exactly the same equation for the airborne pulse, how long will that one take? Well, that's right, once again, it's a fairly simple calculation. It's 1.47 seconds. And this seems to mesh pretty well with our earlier estimate that the sound wave would take more than a second and the water wave would take much less than a second. And so what's the delay between these two pulses? Well, it's simply going to be the difference between these two. So that gives us an answer of 1.13 seconds.